I will show you how the amplitude modulation or AM works. So here's a graphical illustration of it. If this is the signal here, the amplitude modulation will have a fixed frequency, it's oscillating all the time at the same frequency, and yet it mimics the actual wave of the actual waveform of the signal that you want to transform by modulating its amplitude. So if this becomes a complex wave, then the envelope, the outer edge of this wave is called an envelope. See, wave is going up and down all the time, but you can see the contour of it. This is the is called the envelope of a wave. So this envelope of the wave matches the signal you want to produce. So obviously, the carrier signal, the one that is underlying this busy going up and down signal, will have to be much busier than the signal you want to transmit. The way it's done is this. If you look at it, this is the carrier wave. They use the sign here, but it would not have mattered. In more advanced mathematics, you will have e to the negative it, which expands to cosine plus sine, I sine expansion. But here they used sine here. So this is the busy signal you saw that was going busily inside here. This busy going up and down is that this cosine. So W sub c, the omega sub c would control that. The phi sub c is it's a phase shift, which you can discard for now. And this is the amplitude of it. For simplicity in this case here, they assumed c, the amplitude, to be 1, and the phase shift to be 0. So therefore, you get just a pure sine wave. So that would be just sine omega sub t. So that's the signal that is underneath. And then what about the voice signal that you want to carry? They used this one here. They used cosine in this way. So it could have been sine easily as well. And then it also goes through the same transform. In this case, they preserve both the phase, phi, and the magnitude. So here's the catch here. You have this voice signal going here. Normally, you would just multiply the voice signal with the carrier signal and get the answer, get the modulated wave, as you see here. But they could add that extra A. Here we go. This extra A, then what do they call it? Well, they just called it A here. Oh, here. A represents the carrier amplitude, which is the convenient way we could choose to demonstrate the modulation index. Modulation index is coming up a little later. So this is what you get. So if you look carefully, this is the voice part, and this is the carrier part. And you multiply that, and you get the signal. And how much you modulate and all is defined by m over a. A is the m is the signal strength, that is your voice amplitude moving up and down, and this is the just constant added to it. So because it's added there, your voice going up and down will not hit 0 anymore. So you have this waveform which is not like this, which goes to 0 as it should. This would have been the waveform here, but you have one that is just not going down. Okay, in my demonstration I will show you so you will understand that.